So in this presentation, we cover the general solution to one of the most commonly seen LP problems, the assignment problems. And you see problems such as these ones many times in industry. When you want to assign resources to tasks, or you want to assign machine to jobs and so forth. Let's discuss the general formulation for one of the most typically encountered problems in industry, which is the assignment problem. An assignment problem is sort of like a variation from a transportation problem in a way that you're going from a point A to point B. Okay, for example, you have a set of you have resources that you need to assign to tasks, so you need to make the optimal assignment of resources to tasks that minimizes some cost function or maximize some profit function. Okay, so let's discuss this assignment problem. Let's do that through an example again. So we have this company, LDO company, manufactures baseball gloves for the Florida Marlins professional baseball organization. There are 4 categories of gloves. So we have an infielder glove. We're going to call this job number 1. We have an outfielder glove. We call this job number 2. We have a first baseman glove. We call it job number 3. And we have a catcher's glove or a mitt, and that's called job number 4. So we have 4 different jobs. The company just received an order to manufacture 10 gloves of each type. Okay, so 10 infielder gloves, 10 outfielder gloves, 10 first baseman gloves, and 10 catcher's gloves. Okay? The company has 4 machines, and each machine is capable of producing each of the different types of gloves. So each of them can produce an infielder glove, or an outfielder glove, or a first baseman glove, or a catcher's glove. So each of them is capable of doing the 4 different jobs. So the company owner requires each machine to be assigned to one job. The time to manufacture each type of glove is the same for each machine. So in other words, machine number 1, if you take 1 hour to manufacture an infielder glove, machine number 2 is going to take the same amount of time, the same processing time, 1 hour. So that doesn't differ per machine. Now, the time that it takes to set up each machine is a function of the type of glove to be produced. Okay, so we see this in the table, where we have, for example, the setup time for machine number 1 to do job number 1 is 14 hours. Okay, setup time for machine number 1 to do job number 2 is 5 hours. To do job number 3 is 8 hours, and for machine 1 to set up machine 1 to do job number 4, it takes 7 hours. And the same thing for the other machines 2, 3, and 4. So you're given setup times in here, and that differs. So the processing time doesn't change per machine, per job, but the setup time does. Okay, so you have been hired as a consultant for the company to help them with the following decision problem. What is the best policy to complete the 4 jobs and minimize setup time? And what you have to do is formulate an LP solution for this decision problem. Okay, so you have to make assignments in order to minimize setup times. That's your objective right there. Okay, so the idea is, am I going to assign machine 1 to job number 1, or job number 2, or job number 3, or job number 4? And am I going to assign machine 2 to job number 1, or 2, or 3, and 4, and so forth? So you have to assign. You have 4 machines, and you have 4 jobs. So that's a balanced problem. Okay. So we know that the objective here is to find the best policy to complete the 4 jobs and minimize setup times. We know that, and that's the first step to understand what is the objective, and that's clearly stated in the problem statement. Now, we have to define the decision variables. In an assignment problem, the decision variables are what we call 0 to 1, or binary valued variables. If you think about this problem as a decision maker, as an analyst, what you need to make a decision upon is whether you assign jobs to machine number 1, or 2, or 3, or 4. Okay, so the decision variables in this problem becomes a double subscripted variable, similar to a transportation problem, where you define x sub ij equals to 1 if machine I is assigned to meet the demands of job j, or 0 otherwise. Okay, so in other words, x sub ij is equal to 1 is a binary value variable that represents if you make an assignment of a machine to to a particular job. 0 otherwise. The objective function is defined, again, in terms of the decision variables in here. So what you're trying to do here is minimize setup time. So you know that your coefficient of the decision variables are going to be setup times. So we define the linear function, linear objective function, this way. You want to minimize setup times, and your objective function then becomes this linear function represented here. So you want to minimize that. So this linear function gives you the total amount of setup times in hours, okay, on a decision. So it takes 14 hours to set up machine 1 to do job number 1. It takes 5 hours to set up machine 1 to do job number 2, and so forth. And this, all these values are taken from the table that was provided in the problem statement. So this is the function that we want to minimize. The constraints to this problem, let's define two sets of constraints. The first ones are that you cannot assign a machine to more than one job. Okay, and this is very important. For example, this constraint number 1 specify that machine number 1, which is represented by that 1 in the first subscript of each variable, cannot be assigned to more than one job. Okay, so if machine number 1 is assigned to job number 1, that means that this variable x sub 1 is going to be equal to 1, and the rest are going to be set to 0, because you cannot assign that machine to do more than one job. That's why the sum of these decision variables must equal to 1. The same thing for machine number 2, 3, and 4. Notice here, machine number 2 cannot be assigned to more than one job either. Okay, so the summation of x21 plus x22 plus x23 plus x24 has to be equal to 1. So that means that machine number 2 has to be assigned to do a job. And the same thing for machines number 3 and 4. Now, if you leave the solution, the formulation like this, notice that you are not constraining the number of machines that are working the same job. For example, if we see constraint number 1, say that this x sub 1 value is set up to 1. So that means that machine number 1 is assigned to job number 1. Then all of these variables are going to be set to 0. Okay? Now, this doesn't constrain the fact that this variable, which is machine number 2 assigned to job number 1, can be set up to 1 because you haven't constrained your formulation, your solution for that. Okay? So we need to add a set of constraints to take care of that. Okay? So that only one job can be created, can be assigned. I'm sorry. So let's look at constraint number 2. Constraint set number 2 specifies that you cannot assign a job to more than one machine. Okay, and this takes care of that problem that we just saw in the previous slides. Okay, so the previous set of constraints deals with the job that were assigned to each of the machines. So a machine cannot work more than one job. And this one says that a job cannot be assigned to more than one machine. So in here, we set it up for job number 1. Job number 1 is represented by the 1, the second value of the subscripted values here. So x11 plus x21 plus x31 plus x41, they have to be equal to 1. That makes sure that job number 1 gets assigned to at least one machine, gets work. Okay? And the same thing for each of the different jobs. So this is a constraint for job number 2. Means that it must be assigned to at least one machine. And the previous set of constraints specify that at least a machine can only do one job. So this takes care of the whole problem, and what we're saying is that each job must be worked and each machine can do only one work at a time. Since we have 4 machines and 4 jobs, we're just going to have to assign one job to one of the machines. One job per machine. The last constraint are the binary constraints, or the non-negativity constraints. In here, our decision variables can only be 0 or 1, and we have to specify that way. So we say that our binary constraints, non-negativity constraints, are x sub ij is equal to 0 or 1. And this is for all i's and for all j's. In general, in this particular problem that we saw, this assignment problem is a balanced transportation problem in which all supplies and all demands are equal to 1. So that's what I said in the beginning, that LP assignment problem. That LP assignment problem that we saw is sort of like a variation to the transportation problem that we saw before.